Hello everyone, I'm Ismail Renkicukali from UPC Barcelona. I'm glad to have the chance to present our recent research at this conference, where I'll be sharing our work on LiDAR-IMU perception for real-time dynamic obstacle detection in complex urban environments. This project was developed together with Dr. Laia Pagues, Professor Miguel Ferrando, and Professor Luis Jofra, and it focuses on building a lightweight yet robust perception system to ensure safe, autonomous navigation in crowded city areas. Autonomous mobility in cities is really challenging. Unlike highways, urban streets are unstructured, dense, and unpredictable. You have pedestrians moving erratically, cyclists, e-scooters, narrow alleys, and frequent occlusion between these obstacles. Most prior research focuses on structured roads like highways, using heavy, expensive sensor arrays like multiple LiDARs, radars, and cameras. We wanted to challenge that approach by asking, can we build a low-cost, minimal sensor system that still performs well in these environments? This research is deployed on ONA, as you can see in the figure 2, an autonomous robot designed for safe operation in Barcelona's city center. Our objective was really simple: to enable real-time 360-degree dynamic obstacle detection using only LiDAR and IMU sensors. By addressing this gap from research focused on structured road settings. To achieve that, we contributed the following modules: 360-degree LiDAR fusion, ground segmentation, adaptive clustering, ego motion compensation, and dynamic tracking. And this pipeline improved dynamic detection by approximately 30%, while maintaining over 80% accuracy in static filtering. In table 1, you can see the sensors that are used in our system. We used two 3D LiDAR sensors, that one is in front of the robot and one is in the rear of the robot. And we also use two IMU sensors. The information that comes from these IMU sensors merged into one ROS topic. The process starts by merging point clouds from front and rear LiDARs for 360-degree awareness. The IMU provides the motion data, which we use to compensate for the robot's own movement. From there, the pipeline segments the ground, clusters potential obstacles, filters out static structure, and tracks dynamic ones using ego-compensated velocities. Here is a closer look to our methodology. So we applied these 5 steps in our system. The first one is point cloud merger. We merge and filter LiDAR data, discarding points beyond 15 meters to reduce noise. This threshold actually can be changed due to the environments. In maybe more structured environment, you can reduce this threshold to reduce the noise further. And maybe in more complex environments, you can increase this threshold to be aware of the environment fully. But of course, it will increase the computational overhead. But you can decide whatever you want in this case. And also, we merged these point clouds with TF2 transformations. The second one is ground removal. After testing high-frequency methods, standard Brandstack algorithm gave us the most reliable real-time performance. The third one is adaptive clustering. It prevents over or under segmentation by adapting thresholds based on object distances. The fourth one, and the most important one in our research, is static classification. We added this module to further improve the dynamic tracking part, because as you know, the Kalman filtering and Hungarian algorithms are the most common ones in this area. And with static classification step, we further improved the accuracy of the results. So in static classification, we used 10 frame history and IMU motion data. And by this way, we reliably identify and ignore static objects like parked cars and walls. And in the last part, in dynamic tracking, we use a Kalman filter and Hungarian algorithm to assign IDs and estimate object velocities to avoid false dynamics caused by robot's own rotation. So to evaluate the system, we tested in two very different settings. So the first one is actually the Campus Nord, which is the Polytechnical University of Catalonia's main campus. It is structured, flat environment with low pedestrian density. It was ideal for baseline testing and tuning, so it was really important to test our model first in this environment. And also it consists minimal noise, as you can imagine. And the second one is El Born district in Barcelona. So if you ever been into Barcelona, this is the most historical landscape in the area. So it's densely populated, highly dynamic urban structure. So there is a lot of pedestrians, bicycles, and scooters. So these types of obstacles introducing noise, occlusion, and much more dynamic behavior. So these two testbeds allowed us to ensure robustness in both controlled and challenging real-world scenarios. So here's an example of what the system produces. From the LiDAR input, we remove the ground, cluster objects, distinguish static from dynamic ones, and finally visualize tracked obstacles with bounding boxes and unique IDs. So in figure 6, you can see it is the raw LiDAR data that comes from directly our LiDAR sensors. This is the merged point cloud output. The second one is the figure 7, is the after ground removal and clustering, we have this output. In the figure 8, you can see the bounding boxes method. So in here, the green boxes actually means that the boxes are matched from previous history. And so these are the static ones, and the colored boxes are the dynamic ones. And in figure 9, you can see these are the static object clusters. Figure 10, it is dynamic object clusters. These are two different point cloud topics. And the figure 11 shows the system result that shows IDs and green or red markers on obstacles that shows green for dynamic ones, red for static ones. And also these are the qualitative results for Elborn. So in both environments, the pipeline successfully filtered out non-moving structures and consistently tracked moving pedestrians and vehicles even under heavy occlusion. So summarizing the results, adaptive clustering proved stable across near and far distances. Static filtering achieved over 80% accuracy, reducing false positives dramatically. So dynamic tracking captured even slow pedestrian motion, which was really crucial for urban safety. And all of these modules runs at 10 to 15 hertz on compact robotic hardware, showing that it's suitable for real-time applications. In conclusion, we developed a full LiDAR-IMU-based perception pipeline that is modular, sensor efficient, and reliable for real-time dynamic obstacle detection in cities. That said, LiDAR alone has own limitations, as you know, particularly with occluded objects. So what we plan is maybe we plan to fuse additional sensors like cameras in a late fusion architecture, which is the most common one in the industry. Integrate lightweight CNNs like YOLO for semantic classification and merging semantic information and geometric information together. And also apply trajectory forecasting models with machine learning applications to predict pedestrian intent, further improving safety, which can be a really interesting topic. And of course, before adding cameras, we'll ensure strict GDPR compliance for privacy in public spaces. And these are all the references that we used in our research. And thank you very much for your attention.